Hello, grade 11s. I'm talking to you, and who are you? Okay, right, so this is how the ed puzzles work. We get to ask questions, and there are not going to be too many here, but because I know you're watching and pausing, but it is a nice way to do it, so I will put in some questions. So f of x equals cos x minus 45. And we've got three functions that we're going to look at, and we're looking at p, which is this value here, and we're looking at b, a change of period, which we're going to look at for the tan function. So let's see where we can start. F of x equals cos x is our most basic graph. So I'm going to start drawing the negative x-axis because we're going to be heading towards that. So we've got our xy, and first question is, what would, let's do it in a different color here, what would y equals cos x, the basic graph, look like? And let's throw in a question to say, what is cos of 0? Okay, cos of 0. Now, might not know, so you want, how does this graph start again? Well, remember, I keep saying the calculator's there as a nice crutch just to help us to go, cos of 0, oh, that equals 1. So we got that in the background, so we can go, well, I know this graph must start at 1, and go and make it sway along like that. And this is just our rough sketch, so I'm going to put, it goes from 1 to minus 1 there. Every 90 degrees something happens, so this is at 90, 180, 270, 360, just roughly what happens, 0. Now, the x minus 45. Now, 45 is our p value, and it's x minus 45. Given what you know about parabolas and the other functions where we looked at p, what do you think p will do? Do you think it's going to move it left, or do you think it's going to move it right? Okay, so what did you go for, left or right? Well, remember we said it almost feels like it does the opposite. So minus 45 means that it's going to move right by 45. And we can always just use our calculator to check, which we'll do in a second, of course, but this is moving right. So instead of starting there, it's going to start at 45 here, and everything's just going to be exactly 45 degrees to the right. So we won't quite get there, so it would go like that. And this part, this function, if we carried it on, would carry on like that, so it must start dipping down already. So in other words, we're saying that it's going to start lower than 1, and that everything's going to be 45 degrees to the right. So we're saying that that point there is 90 plus another 45. So this is at 135, 0. And again, we can just check it. But we're going to check with our calculator and use our wits to go, well, if we input 135, so if we put cos of 135 minus 45, are we going to get 0? If we are, then we're good. Well, what is 135 minus 45? Well, that's 90. We know that 90 was 0. But calculator to check, cos 135 minus 45, close our bracket, equals 0. In other words, when we input 135, we should get an output of 0, this x-intercept. So it's matching up. Everything's just moved right by 45. So our p-value is 45. So everything's just moved right by 45. Looking straight at the function, there's a negative 45. So it does kind of the opposite. And instead of going left, it goes right by 45. The same as we did for the parabola, hyperbola, and exponential function. All the same. Okay, so draw your graph. Let's draw it a bit neater. And you saw I put a note there saying, yeah, draw it, pause, and give it a go, and then check out how it's drawn here. Instead of just watching it and drawing it with me, you should have a sketch down, because if it's a little bit wrong, that's great, then you got more learning. So we've got this, and we said that it's going to start here, and it's going to go up to start with, and then it's going to go there, and then it's going to be there to almost carry on. Got these intercepts. We've got an intercept here. We've got a high point, local maximum, local minimum, and the ending point. So this is going to be 360. This is x is 0. And we said, well, everything's just moved right by 45. So fill in the other bits. Okay, hopefully you've filled them in to say, well, this bit 0. In fact, let's do the bits that moved 45. So I already said that was 135. This one on our original graph was 270. So we're just adding another 45 to that. So 315. This y value is going to be the same as this. These points here, we just need to work out, well, this was at 180 and it's moved right by 45. Was it minus 1? This was at plus 1. So 180, just add another 45. This was at 0, it's moved across by 45. And our last bit, this starting at end point, calculator is definitely our friend here. Just input 0. So cos of 0 minus 45, because remember it's x minus 45. So when x is 0, root 2 over 2. Okay, root 2 over 2. So a matter of interest. What is that value really? 0.7. Okay, so less than 1. That fits in, and this will be the same. But if you don't trust me, then just punch it in. What do we on? Cos 360 minus 45 equals root 2 over 2. Okay, so there's our process. Similar process for the other two. So g of x equals 2 sine x plus 90. So first things first, got our set of x's. Let's just carry it on in the negative direction and draw the graph of y equals sine x. Let's throw a question in here. What is sine of 0? Cool. Well, I don't know if I agree with you. Let's just check. Calculator, sine of 0, 0. So in other words, it starts at 0, which means we know that it's this graph. Okay. Interesting points along the way. We know happened every 90 degrees. So it's 0, 90, 180, 270, 270, 360. Okay, so x plus 90. Our p-value this time, because we're going to do what's in the brackets first, and then we'll do the timesing 2. But first, brackets, exponents, division, multiplication, addition, subtraction. So our p-value here is negative 90. Remember, it's x minus p. But it looks like x plus 90. Well, it is x plus 90. So a question, is it going to move left or is it going to move right? Well, the negative 90 means that it's going to move left. The plus here, it's almost like it's going to do the opposite. So it's going to move left by 90. Now this one's a bit more interesting. So let's see. We're now looking at what is y equals sine x plus 90. We're not multiplying it by 2 yet. All we're doing is this horizontal translation. So let's move it left by 90. Well, this point here was at 90 degrees. It's going to move left by 90. So it's going to sit right on that axis. Everything's going to move left by 90. So instead of that x-intercept being at 180, it's going to move left by 90. It's going to go over there. This point here is going to move left by 90. The 360 is going to move left by 90. And if this graph had carried on, then it would have gone up like that. So this new point here is going to move left by 90, and we know that it always kind of ends off where it started. So we can see the shape from there. It's going to do that. Interesting how it looks very similar to y equals cos x, doesn't it? And there's kind of planting a seed here. Y equals cos x. These two graphs are exactly the same. Okay, but that we're going to need a bit later in the syllabus. Okay, so we've got that, and then finally this bit here is timesing it by 2. In other words, it's just stretching it up. So instead of going up by 1, it's going to go up by 2. So it's going to start up here at 2. And instead of going down by 1, it's going to go down by 2. So it's going to be stretched by 2 down. So this part here is going to be sitting further down. This part is still going to be sitting at 0, 0, and this is going to be up there. Okay, so draw out the sketch showing all the highest and lowest points, the local maximum and minima, and the x-intercept and the y-intercept. Okay, so I'm trusting that you've got a sketch down here. Here it is, x. We're not going to draw it in the negative, but we're going to have it there ready. I'm going to say, okay, this one started up here and ends over there. Got all these interesting points there, there, there. Already worked out what these were. 90, 0, 270, 0. We know this is halfway. What's the y value of this point? Okay, well, maybe you said -2 because you knew, well, it just stretched out by 2. Maybe you just got your calculator out just to double check it and went, what's 2 times sine of 180 plus 90? In other words, 2 sine x plus 90. So when our x is 180, -2 is our output. Cool, so that matches out with what we said. This bit here we said it moved up by 2, so we think that it's going to be a 2. Makes sense that it's going from -2 to 2. And I think it's just worthwhile checking this often. So 2, not cos, 2 sine x is 0 plus 90. So when x is 0, y is 2. Cool, that matches. And I'll leave you to check that last one. Okay, so we've just translated the graph. Got our calculator there just to check it. Okay, last graph. We're given h of x equals tan 2x. And this bit here now, what this 2 is going to do is it's going to change the period. In other words, it's going to change how often it repeats. So let's start with our basic function of y equals tan x. So let's go for, let's go blue. So y equals tan x is our starting point. Okay, y equals, let's start with what I often seem to ask you. What is tan of 0? In other words, where does this graph start? I'm saying start in inverted commas because it goes each way, but infinitely. But where does it start? What is tan of 0? Okay, so you're still with us. Tan of 0 is 0, so it starts at 0. With tan, they're asymptotes, and we're going to draw asymptotes first. We did the same thing with hyperbolas and exponential functions, and we're going to do the same for tan functions. Let's join our asymptotes and say, well, the interesting points seem to be in our trig functions 90, 180, 270, and 360. Seemed like that was going to be the same as that. So let's plug in and see. So what is tan of 90 degrees? Tan of 90. No, it's not math error. That's not actually what it is. It doesn't exist. It's undefined. So in other words, there is an asymptote there, and if we remember, there's an asymptote there, and this is also 0. So we know that our general tan graph looks like that. Carrying on, carrying on, carrying on. Now, what does this 2 do? I said it changed the period. In other words, how often the function repeats itself. At the moment, it repeats itself there carries on, then starts repeating itself. So every 180 degrees, it's repeating itself. The sine and the cos function were repeating themselves every 360. Look, we got there, and then 360, and it will start again. And this graph, there it starts, 360 degrees later, it starts again. Okay, so for this one, changing the period. Well, let's put in some interesting values here. So we're going to put in, and I'm going to draw this, just have our graph ready to sketch our final version, x, y, and let's go over there, and we said that we had interesting points at 90, 180, 270, 360. So let's see what happens now, and obviously at 0. So what's tan? Now we're going to look at our graph that we are required to draw and say, so what is tan of 0? So 2 times 0. Well, that's just going to be the same as it was, right? So that's going to be 0. In other words, what is tan of 2 times 0? When we input 0 into our function, what do we get? 0. Okay, let's keep looking at these 90, 180, 270. If we input 90 into our graph now, y equals 2 times 90. That's going to be the same as tan of 180. Tan of 180. So we should get 0 as our output. Let's check it out. In other words, tan of 2 times 90, when we input 90 into our graph that we're given, it will be the same as looking at our original graph, y equals tan x, what happens at 180. So we've got tan of 2 times 90, in other words, tan of 180, which is 0. Okay, interesting. That was at 180, it's happened twice as quickly. Right, so let's see what happens at 180. What's tan of 2 times 180? Well, 2 times 180 is 360. So what is tan of 360? Should also give us 0. So it seems like these are happening twice as often. X-intercepts were at 0, 180, 360, now they're at 90, 180, 270, 360. So everything's happening twice as quickly. So where do you think these asymptotes are going to be? Well, yeah, they're just going to happen twice as quickly. So instead of happening at 90, it's happening here in the middle. And it's going to happen in the middle of each of these. So instead of happening at 270, it's going to happen at half of 270, 135, there it is. So this is at 45, this is 135, then we've got another one here, and another one here, and then we have our graph. So we just said this happens every 45 asymptote, 45 x-intercept. 45, 45, so 225 plus 45, 315, and then our shape is the same, it's just been squished up a bit. So same shape, oh, missed it, same shape, same shape. And let's just put these arrows to show, look, we're carrying on forever and ever. So that's it. That's what the change of period, and the same happens for the sine and the cos graph. If you said sine of 2x, it would just repeat twice as often. Okay, those are our ones for today. Tomorrow we're moving on to what do we call the fundamental trig identities and reduction formulae, and through that we're also going to revise the cast diagram as we did just before half term. So enjoy. See you in class soon.